Hi, my name is Nick Fazzari, and I'm on the Sloan Sports Analytics Conference Research Papers team. It is my pleasure to introduce Andy Miller, who wrote a paper with Luke Bourne called Possession Sketches, Mapping NBA Strategies. His presentation will last 20 minutes with a 5-minute Q&A afterward. Just raise your hand and I'll run over the microphone to you. And with that, Andy Miller.
Thanks, everyone. I'll get to it. Oh, yeah, I got to do both here. So the high-level goal of this project was to organize a database of basketball possessions by the offensive structure in that possession. The motivation behind this was to answer questions like these. How do the Rockets create kind of all their corner threes? How would we go about searching the kinds of offensive structure that lead to corner threes? What is the success rate of certain types of plays like the Warriors weave? Which players run these plays kind of more efficiently? So all of these questions are contingent on a certain type of structure, like the weave set or certain types of cuts. So to make this more concrete, let's deconstruct a few possessions. So here's the Spurs hammer set. And the actions that characterize a hammer set are this kind of quick give and go from Ginobili on the left side, the drive from the left wing to under the basket. Meanwhile, Danny Green is cutting from the right wing to the right corner. And then while he's doing that, a big is pinning down his guy. So these kind of sub-actions are the structure of the play. So let's look at another example of the weave, or of the hammer set. So here the structure in this that characterizes the weave are these kind of little cuts, these little reverses along the three-point line. And then finally, Klay Thompson gets the ball and either takes advantage of some space to hit a three, or sufficiently separates from his guy, Peyton in this case, and then threatens toward the basket. And then the attack is taking advantage of the switch, giving Bogut the easy alley-oop. Okay. So the structure that I pointed out is characterized by these individuals performing actions and the interactions between teammates. And we only saw kind of two examples here, but there's a wide variety of offensive structure. And that's kind of what makes the game really, really exciting. And that also makes the challenge of organizing it very difficult. So why do we want to do this? The sort of first order thing is that this organization can help with many day-to-day tasks, like simple similarity queries. Let's say we want to get all of the hammer sets that the Spurs ran. It'll save time sifting through video. And furthermore, we can, if we're kind of building out a vocabulary of basketball actions, we can start recognizing patterns and start labeling complex actions. Importantly, this also opens up the ability to ask new questions. So some of the questions that I alluded to on that first slide. What kind of plays lead to high probability shots? We can start building out models that explore player and team habits. And we can start building out models that are aware of context, as long as we define those contexts. So this presents a few challenges. Offensive structure varies systematically in a lot of ways. There's temporal variation. Danny Green isn't making that cut at the same speed, kind of in every iteration of the hammer set. He's not cutting in the same exact location. It's certainly close, but not exactly the same. And the interactions between players, the kind of choreographed cutting between Danny Green and Manu Ginobili isn't exactly the same in every iteration. So handling this sort of variation requires flexible models, but we want to use this model to explore possessions, and kind of balance is another challenge. So some existing projects have looked at offensive structure. They focus largely on answering these sort of yes-no questions. Does this play have an on-ball screen? Does this play have a pick and roll? Which class is this possession from a kind of pre-labeled discrete set of classes? This often requires labeling a lot of known sequences, so like hundreds to thousands of sequences. And this also looks, importantly, this requires us to look for known structure. We have to have a definition of what we're looking for. Which kind of 10 plays are we going to classify each possession into? But in this work, we're looking at kind of an unsupervised structure discovery. There's less human intervention. There's no labels in this instance. We're kind of building out a vocabulary of basketball actions. And this allows us to make global inferences and kind of look at every single possession, a model that touches every single possession and shares information from between every single possession. And crucially, we'll focus on building out interpretable models. Okay. So to understand this method, let's look at kind of a related organizational task. Let's organize a large corpus of documents. So let's say you have about hundreds of thousands or millions of news articles, and we want to suggest related news articles. So we can see here that maybe the top two, the first one is about Trump and healthcare. The next one is about Jeff Sessions probably committing perjury. The next one is about McElroy playing golf with Trump. The next one is about Kaepernick's kind of national anthem protest. And then we see an article about like the University of Texas basketball team and then the NCAA tournament. So all of these articles are sort of about politics generally. And all of these articles are about sports. And this is what topic models do. They go in and they find kind of the structure in a large set of unstructured documents. And the structure are these topics, these kind of global topics that describe the content of every single article. And importantly, they also describe, for each individual article, how much of each topic are you. So you can see some of them are just politics, some of them are a mix between sports and politics, and some are just related to sports. So there's a rich topic modeling literature, which is why we're kind of shoehorning this problem into a topic modeling problem, because there's a lot of models, there's a lot of development, there's a lot of algorithms for doing this, because this is like used to, say, organize newspapers and the web, the internet. So the question is now, how can we adapt these methods to organize basketball possessions? For instance, some possessions might be weaves, some might be hammers, some might be kind of weave-like. They might have elements of a weave, some might have elements of a hammer set. So we need to represent a possession as a document somehow. So let's look at the hammer set again. How would you describe the sequence of actions that collectively compose the hammer set? Well, I kind of did this earlier. There's like a cut to the left wing, a little give and go, a drive from the left wing to the basket, and then a weak side cut to the corner. So we can kind of collect all of these little descriptions into a single document. And this document describes the structure of the play. We can do this for every single possession we have. So for instance, if we have 200,000 possessions from the 2014 to 2015 season, we can do this for every single possession and kind of build out the document for every. This third one is an instance of the weave play, so its document is distinct. It's quite different from the first two. So in each document, cut to the left wing is like a word in the vocabulary of basketball movements. And in English, we kind of string together words to build up higher level concepts. Similarly, in basketball possessions, these little words build up higher level concepts that are like the hammer set or the weave or pick and roll. So now, in topic models, we have a vocabulary. The algorithm looks at words and determines the topics and determines how much of each topic each article is. But for basketball sequence, we have this desired vocabulary, but we don't really have a way of getting it, because what we have is player tracking data, is what I'm looking at, is player tracking data. So this is about less than a half of a second of a single possession, one possession among 200,000. So there are about 1 billion kind of X, Y, T points that I'm looking at in this analysis. So the first order task is to build out this vocabulary of actions. We want to translate this player tracking data into which part corresponds to a cut from the wing to the basket, which part corresponds to a cut from the right wing to the corner. And then we can use these actions that we've inferred to build up a higher level representation. So this is what the project really is. It's two parts. One is a model of individual action, a kind of data-driven vocabulary of basketball. And the other is like a topic model-based model of the interaction between individual teammates' actions. So for example, an individual action could be Ginobili driving from the left wing to the basket. An interaction would be Ginobili driving from the left wing to the basket while Danny Green is making a cut on the weak side. And just to jump ahead, something's not rendering correctly, but just to jump ahead, there are about 6,000 dots that you probably can't see, I can't really see, and a bunch of red dots. So each dot there represents a single possession. And there are 6,000 Warriors possessions that I've analyzed in this set. So I'm kind of looking ahead to see what kind of artifacts we can build out of this and how we can systematically explore possessions. So here I've highlighted 2 individual dots. And those 2 possessions, they're close by in this space. And that means that they overlap a lot in terms of semantic structure. And in fact, we'll see that weaves cluster. And furthermore, individual types of weaves cluster, where one weave that finishes with an attack to the basket is more similar to those weaves, and another weave that finishes with a three-point attempt is similar to those types. So, but the first thing I'm going to do is go over the individual action model. So within a single possession, I'm viewing a player's trajectory as a sequence of multiple actions. And so Harrison Barnes here, he's starting up. It's hard to see. I think I rendered a court very lightly, but he's starting up around the elbow, the right elbow. He's going up above the three-point line, and then he's cutting down to the left corner. So this sequence is made up of multiple actions, and where these actions kind of start and stop is where Harrison Barnes himself starts and stops. So when his speed reaches some low point, I'm kind of determining that that's one discrete action, and I'm cutting the sequence there. So this is sort of a pre-processing step. So we can do this for every single player trajectory, and we'll get a representation of a possession that looks like this, where each player is represented by their discrete action that they're performing at any given point in time. So Harrison Barnes here has about 7 or 8 little actions, and his representation of those kind of 7 or 8 discrete actions. So each action is characterized sort of by its spatiotemporal shape. So what we did in this first part is build a model of that spatiotemporal shape. In this instance, we kind of pulled some ideas from animation and video game development and modeled each of these trajectories as a Bezier curve. And the different actions that a single player can take, we incorporated a mixture of Bezier curves. There are many, many Bezier curves that could represent all the kind of various types of actions that individual basketball players make throughout the course of a possession. So here we've looked at 2 actions. But really, I'm fitting a mixture model of about 250 clusters. That segmenting procedure that I described a few slides ago resulted in about 4.5 million trajectory segments over the course of the season. This was a pretty large data set, and I used expectation maximization to fit this model. And because it was so large, it took about 21 days of compute time on a parallel machine. And the results are things like this, where I'm calling these action templates. So these are 2 examples of clusters that were discovered by just looking at all of these, by fitting this mixture model, essentially. So the dark line that's kind of leaving a trail here is the Bezier curve, is the cluster center. And these dots around them are actual examples from the data. Those are actual cuts that were made throughout the course of the season. So like one of the dots on the left is a James Harden baseline cut. And note that the symmetry here that was discovered was not encoded in the model. It was just present in the data, and it was learned by the model. So here are 2 more examples of different kind of actions. And then, so note there's a little bit of variation and spatial variation around each of these. So we don't have just 4, we have, or just 8. We have 250 of these actions. Some of them are traverse long distances. Some of them are just standing still. Okay, so I'm moving on to the teammate interaction model. So we've decomposed each possession into a sequence, or each player is a sequence of actions. And now we've labeled them. So the result of this player action model is inferring labels for each of these possessions that share structure across different possessions. So this is going to give us a way to discover whether or not 2 plays are hammer sets or 2 plays are weave sets. So now that we have a sort of vocabulary of actions, we're sort of in the realm of being able to apply a topic model, latent Dirichlet allocation, to model possessions. The first thing we need to do is settle on a vocabulary. So what I did in this, case was we could use individual actions as words in the vocabulary. That would be like if we had the word house or white in our vocabulary, and we just kind of treated them independent of each other. But a much more expressive way of coping with this kind of phenomenon is if we have White House, we know that the semantic meaning of White House is quite different from just white and house used on their own. So in the same way, adding bigrams to our vocabulary, I used pairs of actions that are instantaneously co-occurring as the vocabulary words in my model. So that allowed us to capture things like Ginobili is cutting or driving from the left wing to the basket, while Danny Green is starting his cut from the right wing to the corner. And so an example visualization of these pairs of actions looks like this. So we have a few kind of cuts along the three-point line while a cut, say, from the right corner to the top of the key is occurring. And the result of fitting this topic model is a set of global topics that kind of roughly represent strategies. So when we did this for documents, what we got were words that were associated with sports, words that were associated with politics, and then that allowed us to kind of figure out how much of each possession was sports, or how much of each, or document was sports, how much of each document was politics. Similarly, we're going to have these topics that are just distributions over pair actions. So that'll allow us to figure out how much of this possession is kind of topic 1 or topic 2 here. Okay. So now, instead of looking at kind of the topics, I fit 100 topics for this model. But instead of exploring kind of the topics themselves, let's look at the possession-specific loadings. These are the possession sketches that I'm calling. And this allows us to, again, it's a little washed out, visualize an entire season. So as a kind of validation measure, I went in and I hand-labeled about 50 weaves, and I'm kind of plotting these weaves up here in red. And I'm going to zoom in on one of these clusters. So this is a kind of a dimensionality-reduced set of points here, where each point, again, represents a single offensive possession. These are two Golden State possessions, so that's actually 2 points that are very, very close to each other. And they correspond to these 2 plays. So we see they're Warriors weaves. We see that this top weave ends with a Barbosa attempt from straight on. And this bottom play ends with a Klay Thompson 3 from just to the right of the top of the key. And it's easy to see kind of how similar they are by looking at their kind of spatial signatures next to each other in the raw data. But there were other clusters of weaves. And so that should have zoomed in on kind of the cluster right below. And this was a different type of weave play, where the action that kind of makes them distinct is that Klay Thompson is able to beat his man and threaten towards the basket. And this forces a switch. And this kind of different offensive structure was picked up on. I think it's a lot easier to see when we actually look at the data. If we look at Klay Thompson's trajectory here, he's curling around and actually kind of forcing a switch. So that's what I think the algorithm is picking up on as the difference. And another way of using this sort of output is we can look at kind of a map of all of the ways that corner threes happen. So what I'm showing you here are all possessions from the Warriors, Rockets, and Spurs that ended with a corner 3. And this is the possession sketch map. And all these clusters represent different ways in which those corner 3s came to be. So let's look at one of these, this left cluster here. That's at the bottom here. I'm kind of projecting it to the left. So this cluster, it turns out, is characterized by this sort of penetration along the left side to a kick out to the right. And there's a little bit of waffling here. There's the kind of the end action is slightly different. This one will be a lot cleaner. But what brings them together really is the penetration on the left side. So on the left it was Thompson, on the right it was Curry. And it's really easy to see their similarities here. So the sequence of actions was slightly different, but the spatial signature was very similar. And so looking at that top cluster, we'll see a totally different way of generating a corner 3. So here are 2 Rockets possessions that are in that top cluster. And what kind of makes these 2 similar is this baseline cut from the left to the right side that Harden performs. It's kind of more than that. So there's this entry pass to the high post. The point guard comes down, sets a pick for Harden, and Harden makes his way to the other side. So in the first instance, Harden was able to kind of distract Ariza's guy enough to get Ariza a look. And the right, he's able to free himself and get a look from the right corner. And it's easy to see, again, when we look at the actual data. So we'll see that pick, the Harden cut, then Ariza getting free on the left, and Harden getting free on the right. Okay, so these were 2 sort of example uses of this algorithm. So to conclude, we've developed possession sketches, which is a way of organizing like a large database of basketball possessions by the offensive structure present in that possession. And it was built out of these two main components. The first was building out an interpretable vocabulary of individual actions. And the second was modeling the interaction between those actions. Like, how do they co-occur? And then we showed a few ways of exploring possessions, exploring outcomes, and kind of discovering ways that corner threes, for instance, could be created. But I think the kind of development here is that it opens the avenue to ask new questions. Some of the questions that I alluded to in that first slide, like systematically exploring offensive structure is great when we have this sort of similarity metric of offense. And I think that this allows us to kind of, it'll lead to new research opportunities. We can develop context-specific probability models now that we've developed a context. And I'm seeing my time is up, so thank you.
We have 5 minutes now for Q&A.
Yep, thanks a lot. I have a question for you about the modeling. In natural language processing, there's something called stop words that you have to extract in order to get a more accurate language model, a more accurate topic model. Is there an equivalent to stop words in this kind of analysis?
There is.
And how do you remove those?
They were actually literal stop words because there are a lot of words that were caught where players weren't moving at all. Like, players stand around a lot, and kind of that lack of motion wasn't very discriminative. It didn't like kind of lead to good clusters. So I detected, it's easy to detect though, because they're just standing in one space and the velocity is very low the whole time. And you can either combine them into multiple words so that like the value of that word is like downplayed a little bit. But yeah, there are stop words. Didn't show them here, but yeah.
I had a question about the source of the data, the spatial data, and what is the source of that?
Oh, it's a sport view data set. Yeah.
Yeah, I've done some unsupervised learning as well, and I always struggle with the question of like the number of topics. I was just wondering if you can tell us how you chose.
Yeah, there were two sort of tuning parameters here. One is the number of actions too, and then the other one's the number of topics. And I did some out-of-sample likelihood test as a way of tuning that, and then also not letting it grow too large because I wanted to be able to explore them. So 100 is what I settled on, it's 100. But yeah, out-of-sample likelihood test is a way to tune them.
Hey, when you ran the data in the front.
In the front? Where? Okay. Hey.
When you ran the data, did you feel that the screener had more of an impact on the success of a play, the cutter, the shooter, kind of all three?
So this was more of like an organizational. I didn't really assess outcomes so much. But what I did notice were larger movements, like that baseline cut, for instance. Those had more of an effect on the ability to organize or detect that kind of signature of the play. Like smaller movements like a screen were hard to find. They're like kind of low signal and a lot of noise. But, yeah.
Over here.
Hi, thanks. I was wondering if your outcomes and the results of your study were sensitive to the cut points you made in defining the actions. In reading the paper, I noticed that you made cut points whenever the first derivative dropped below a certain point and stayed there for a while.
Yeah.
Did you like test how sensitive it was to that?
So I did not do a sensitivity analysis, but that is actually what I've been working on lately with Luke, which is automatically detecting the appropriate cut points. Because you can imagine some cuts involve stopping, right? So yeah, that's a great point.
And I think we have time for one more.
I was just wondering what you would do to try to address the symmetry aspects of these plays, right? This play was run, it's the exact same as that play, but everything's mirror imaged, and how you manage that.
Yeah, that's a good question. So I think the symmetry of these plays would be derived in the symmetry of the individual actions, and we might be able to do something like detect when so like I showed those two baseline cuts were symmetrical. And we could maybe detect when those two actions are in symmetry, and then that would actually propagate into to the topic model itself. So there could be a way of actually doing this kind of manually, but I didn't encode any symmetries in the model just because it was present in the data and it was just kind of there to be learned. But yeah, you could, I think, in a post hoc way do that.
All right, thank you very much, Andy.
Thanks.